Welcome to Race Course number 97, and today we're talking about the aerodynamics of suspension bridges. And in particular, we're talking about the aerodynamics of one particular suspension bridge called the 516 Aruka pedestrian suspension bridge over the Paver River. So the reason why we're looking at this is because there's been histories of bridges collapsing because of various aerodynamics exciting certain frequencies in them. And we'll cover them as well. So to look at bridge aerodynamics, we're looking at a paper called Aerodynamic Characteristics of the 516 Aruka pedestrian suspension bridge over the Paver River. This is open access, so you can find it in a link in the description. And this is a very long bridge, and they did some wind tunnel testing on it, which is really cool. We'll get into that as well, and how to do some similarity testing and what you need to look out for. So let's get on with it. They say that there are examples of long bridges up to 494 meters. For example, the Charles Kuhnen in the Swiss Alps, which is a maximum of 85 meters above the ground. And these kinds of bridges are equipped with horizontal catenaries at the deck level to prevent excessive swinging displacements. So let's talk about what these catenaries are. So we have a picture, figure one here. If you're watching this on YouTube, then you can see this. Otherwise, if you're listening to this on Spotify, there's also the video on Spotify, or you can go onto our YouTube channel and see the video as well, or download the paper. So what we see in figure one is this really long bridge going from one end to the other, and it's typical where you just have, sags along the bottom a little bit. It's a pedestrian bridge. And then around the sides, like there are two cables, one on each side, and they're very curved, and they run the entire length of the bridge as well. But there are wires going from these cables to the bridge to stabilize it. So some bridges have them, some don't. They say here that suspension pedestrian bridges are also usually use a stiff and straight deck. So hopefully no sagging. However, this picture looks like there's some sagging, or maybe it's just made to look like that. I'm not too sure. They say only very few works on these types of bridges can be found in the literature, as the large majority of suspension bridges are for road traffic. Since the Tacoma Narrows accident, such bridges are usually submitted to wind tunnel tests worldwide. For example, the ones referred to in some references in this paper. So the Tacoma Narrows Bridge, this is a really famous example, and you've probably seen footage of it. Like we always see footage in like science class when you're in like grade 8 or something. And where it's from the 1940s in black and white, where you see this bridge, how it starts off vibrating a little bit, and then it starts wobbling and like twisting, and then it finally breaks after like I think 20 minutes or something. And this is the Tacoma Narrows Bridge, and this was a major problem back then because they didn't know why this was happening, and all these engineers were trying to figure out why, but the old girl kept her secrets. And then finally, one day, an engineer realized that it probably had something to do with the natural frequency of the bridge and the aerodynamics, with the wind that was present, exciting that natural frequency. That's what happened. So we'll get into these instabilities in a little bit, but just for this bridge, what was happening was the wind was going over it, and that was producing some flexing, which then started to amplify because the oscillation frequency of the bridge matched the natural frequency of the bridge. So then this coupled and then just got worse and worse until it just disintegrated. So the bridge under analysis in this paper is a suspension bridge, and it's 516 meters long, which makes it the longest of its kind, and has a 1.2 meter wide deck with a remarkable sag running 175 meters above the Paver River in north of Portugal. Having no deck level catenaries, so those wires on the side of the bridge connecting to the rest of the bridge, makes it unique and has such characteristics that makes it flexible with a swinging displacement first mode of a very low frequency, which reinforces the need for wind tunnel testing. So what does that mean? Because it doesn't have these wires running along to stabilize it, the frequency of swinging for this bridge is quite low, which means that potentially a wind could excite it, and you'd have the same problem happening as the Tacoma Bridge in some sense. So they need to do some wind tunnel testing to see if this will happen or whether it's safe. So the evaluation of the bridge's aerodynamics became an obvious need, leading to a set of wind tunnel tests performed over a scaled section model to obtain static aerodynamic coefficients such as the drag, lift, and rolling moments, and the dynamic response to determine if any instability may occur. So the dynamic response is how the bridge is responding over time, and whether these responses amplify, and then the amplitude of these displacements of the bridge grow to the point where it becomes unsafe. It could break. So these tests were carried out on different bridge configurations. So a deck with people, and a deck with an arch for secondary cables for the static coefficients, and for upward and downward winds. So the wind's either coming straight on to the bridge, or it's coming up at an angle or going down at an angle. So in other words, different angles of attack for the bridge. The wind tunnel dynamic tests aimed to ensure that no aerodynamic instabilities, such as divergence, galloping, flutter, or vortex shedding, were able to occur up to a determined wind velocity. So let's discuss these 4 different principles. First of all, I'm going to say that for aeroelastic instabilities, vortex shedding is not technically an aeroelastic instability because vortex shedding is an aerodynamic phenomenon, and that is part of what causes aeroelastic instabilities. And the reason why is because when you get vortex shedding, this changes the force on the object, which then excites certain motions. So let's talk about divergence, galloping, and flutter now. So I've done a podcast on divergence, and this is where, simply put, if you have an object where you have a wind hitting it or a airstream hitting it, and then this results in a force, this then turns the object to a point where the force that it's now experiencing is even greater. And this additional force then turns the object even more. And this cycle continues until the object turns so much that it just breaks. That's divergence. And it's just a one direction kind of thing where it's not going to be oscillating around or anything. It just keeps twisting until it breaks off. Now, galloping and flutter are a little bit different. These are very similar, but there's a fundamental difference. So galloping and flutter are where an object will bounce around. So we've seen airplanes where the wings are like fluttering around. The Tacoma Bridge is also an example of galloping or flutter. So these are the phenomena. The difference between the two is that flutter needs at least two axes to occur around, so 2 degrees of freedom. Whereas galloping can occur with just 1 degree of freedom. So in other words, it only occurs in one direction or more, whereas flutter needs to occur in at least 2 directions or more. That's the mathematical difference. But in terms of just looking at an object, they look the same. It's just the object is bouncing around and twisting and looking really weird. So these are all different aeroelastic instabilities, and bridges can experience all 3 of these things. So the suspension bridge is supported by 2 reinforced concrete pillars, this one, which are 35.5 meters tall at each end of the valley sides. The bridge span is 516 meters and is suspended through a system of catenaries and hangers. The distance between the main cables increases steadily from the bridge midpoint to the pillars. And then I have some figures here showing the bridges where it's really long and it snakes through like from one end to the other quite well. And then there's a little bit of an enclosure to the bridge that people walk through, and then like these little arches over the top, which the wires from the support system can connect to then give the bridge more stability. So onto the methodology now, we're talking about similitude. So similitude is the term used when we are looking at scaling an object. And this is not necessarily just for scaling down, it could be for scaling up. However, in practice, we always want to scale down because that means it's more practical to use. But the term similitude just means when you're using 2 different scales and you're trying to get the same phenomena, whatever that may be, across these 2 setups. So the similitude theory establishes proportional ratios and the scales among physical entities for dynamic issues ruled by fundamental dimensions such as length, mass, time, or frequency. These scales are respectively lambda, mu, tau, or phi, and they're defined as lambda is the model length divided by the model length divided by the prototype length. And then mu is the mass of the model divided by the mass of the prototype. Tau is the time scale of whatever frequency or whatever is happening of the model divided by the time scale of the prototype. And then the frequency is that phi is actually the frequency of the model divided by the frequency of the prototype, whatever phenomenon you're looking at. These are important characteristics to get the same, or if not the same, very similar between your test object and real life to make sure that you're getting the same phenomena occurring. So they say when considering the wind structure's interaction with the model characteristics, the flow has to be also taken into account, meaning that the flow around the prototype and the model have to be similar. The ratio between the flow inertia and viscous forces and the Reynolds number should be kept constant. So in other words, the Reynolds number is just the relationship between the inertia and the viscous forces. So ideally, you want to have the same Reynolds number in your wind tunnel compared to real life. That's not always the case. For example, in this particular case, and in buildings in general, the wind tunnel, you can't really get the same Reynolds number without running into problems such as compressibility problems. So to explain this a little bit more, let's say you have a massive building and then you want to shrink it down and put it into your wind tunnel. So you might have a scale of 1 to 100. So if that's the case, you need to then have a velocity of 100 times what you have in real life, because your length scale has dropped by a factor of 100. So now you need, if you have a 10 meter per second wind speed outside, that means you need to have 1,000 meter per second wind speed in your wind tunnel, which is obviously like Mach 3. And so that's going to then result in different flow physics occurring. So that's why Reynolds number similarity is not always possible. But that's when you need to get intelligent about what you're doing and think about how the Reynolds number is affecting the flow. And sometimes you can go for a lower Reynolds number and still get the same flow phenomena. For example, if you have a sharp object, the vortex shedding coming off of a sharp object is very similar across a very wide range of Reynolds numbers. And that's because the sharp edges are dictating where the flow is separating. And so that's not really based on inertia or viscous forces. It's more just due to the geometry. And even if you increase the speed of the flow dramatically, the flow doesn't have enough energy to get around those very sharp corners. So you can go for a lower Reynolds number and still get the same kind of flow physics happening. So that's the Reynolds number similarity in a nutshell. They say, due to the small dimensions of the model structure, parts of interest such as the deck beams and handrails, this Reynolds number similarity is not possible to achieve. Nonetheless, as those parts show sharp edges, meaning clear flow separation points, which I was just talking about, the flow distortion and resulting pressure distributions are negligible for Reynolds numbers above 10,000, and the aerodynamic coefficients may be assumed as Reynolds number independent above this Reynolds number, as I was mentioning earlier. This is just not for bridges, but for any object in general. But for this particular case, they can do this. So that means that they can effectively get Reynolds number similarity, even though the Reynolds numbers are not the same, but the flow physics you can assume will be the same or very close to the real life situation. So the atmospheric wind is naturally turbulent, so more complex even in orography. So the test should be simulated on the appropriate scale to the turbulence spectrum. However, as low turbulence flows determine heavier conditions for aerodynamic instabilities, wind tunnel tests performed under low turbulence flows are acceptable as contributing to the safety. So let's talk about this. In real life, the turbulence intensities of winds are very high, like 5, 10, 20%, even higher. In wind tunnels, we usually have very low turbulence densities, depending on the wind tunnel that you have, but the majority of wind tunnels around the world are around about 1%, maybe a little bit less. You can get some which are 5%, 10%, or you can get some which are like 0.05%. So if you're in a wind tunnel with 1% turbulence density compared to the real life situation, which is 10% turbulence density, you're going to get different flow physics. And the reason why that is because turbulence density effectively dictates how poorly behaved the flow is and how variable it is. And a higher turbulence density means that you're going to be getting more turbulence, which means that the flow has more energy to stay attached over curved surfaces, for example, longer, which means that you're going to get different flow separation patterns, which means you get different lift, force, pitching moments, blah, blah, blah. So they're saying here, though, that low turbulence flows, which is what they're using compared to real life, result in worse situations for this bridge. So they can use this wind tunnel still, and if it passes these tests under these conditions, then it will be fine for real life, because these are the worst possible conditions effectively to have a lower turbulence density, because this results in more instabilities. So that's what they're saying here. Even though you don't have turbulence density similarity or Reynolds number similarities, these are the worst of conditions effectively, so it's acceptable. So a little bit more turbulence. Turbulence may also affect the static aerodynamic coefficients, as it may change the shape of the flow streamlines that mark flow separation, and so the drag, as the base pressure values also change. So as I just mentioned there, where it changes flow separation, for example, vortex breakdown, mixing characteristics, wake breakdowns with Reynolds numbers, whatever. So the prototype model behavior similitude requires the quality of all non-dimensional parameters to be obtained from the relevant physical quantities. So in addition to the geometric scale, it is required that the dynamic behavior in the model follows the same laws that the prototype does, even if somehow simplified. The use of a wind tunnel to study the structural behavior of a suspension bridge under the wind load, when inertial forces may play an important role, determines a unitary value for the fluid density and gravity scales, leading to the mass ratio equaling the length scale cubed and the time scale ratio equaling the length scale square rooted. When mass forces are important, as in the present case, the so-called Froude similitude means that only one dimension is arbitrary, the length scale, due to the wind tunnel test chamber dimensions. So let's just briefly talk about this a bit more. So now we're getting into some real difficult similitude properties here. And I can't remember if I mentioned it just before, but often it's difficult to get similitude across a bunch of different parameters. So for example, if you wanted to get the Reynolds number to be the same, but then you want to get another non-dimensional coefficient to be the same, but it has the velocity is now squared in that coefficient. If you were to drop the velocity to get the same Reynolds number, well, the other coefficient that you're looking at will drop by twice as much, or a square as much, sorry. So that means that you can't get the same similitude between two different parameters. You can only get the same similitude if changing the value in one of them changes at the same amount. So in this particular case, the mass ratio is proportional to the length scale cubed. The time scale ratio is proportional to the square root of this length scale. So in other words, if you have an object which is 1 meter and you drop it to 0.1 meters, so a factor of 10, the mass ratio will drop by a factor of 1/10 to the cube, whereas the time scale ratio will drop by 1/10 square rooted. They're different amounts. So you cannot get similitude between these two values. In this particular case, you need to then look at which value is more important for your study. So for an example, in this particular case, you could say, okay, the mass ratio affects the damping, for example. So does the time scale ratio. So which one is more important, and go for it. And you look at the spring constant, like the torsional stiffnesses, etc., and see how that factors in terms of the breakdown or the propagation of these instabilities. So that's where similitude becomes very difficult. And the fact that this author is doing this is really impressive. You don't get this too often. So the author's doing a really good job in terms of making the work very applicable. So let's talk about the model. The model scale is 1 to 4, which is really big, and was determined by attending to the following: the need for enough definition for the deck and handrail beams, the need to avoid the effects associated with the Reynolds number, the need to reproduce a deck module, which is 4 meters, roughly 8% of the full length. Due to its large porosity, it uses 4% of the wind tunnel cross-section, so blockage is not an issue. The Reynolds number, which is evaluated as 100,000 over 100,000, sorry, using the smallest beam dimension, and for the full range of test wind velocities. So they've used a massive section here to test, and even though it's in wind tunnel, it's still a really big section. And they say for the model installed in the wind tunnel, and they have some pictures here, they have one section of the bridge, and they say, in order to keep the flow two-dimensional and avoid three-dimensional effects around the model's tops, thin flat end plates with rounded corners were installed at the edges. And what this does is effectively they're just splitter plates where the flow comes along and then it gets divided into two. One side goes around the entire bridge, one goes through the entire bridge, and they do not mix until later on. So that way you can sort of ensure a two-dimensional flow. And connecting the end plates sets of supports supporting external horizontal beams allowed to suspend the model inside the wind tunnel, the attachment point coinciding with the gravity center. So in terms of the wind tunnel, the test chamber was 1 meter by 1.2 meters by 3 meters. And it had a low uniform turbulence intensity level of less than 1%. However, they say all tests were performed under an open test chamber to avoid blockage. So this is interesting. They give you the test chamber dimensions, but they must be able to take the walls out and the roof out. And it may be a 3/4 open, or I'm not sure exactly which type of opening it is. But they say it's an open test chamber. So that means that you can put a bigger object in there without getting blockage effects. They say that the wind velocity speed was evaluated using a 5mm pitot Prandtl tube. And I just wanted to point this out because it's a term that you don't come across too often. Usually a pitot Prandtl tube is called a pitot-static tube. They're the exact same thing. It's just that Prandtl and static, they're just different names for those holes around the edges of the side of the pitot-static tube, whereas the pitot hole is the one at the front. So let's move on to the a bit more of the setup of in terms of the people. So they have the bridge deck, the cutout, and then along the railing of the bridge, they then have like cardboard cutouts of people, and then they've zip tied them to them. So they're two-dimensional cardboard cutouts, and they are to simulate like a family. Then there's a guy there walking his dog. So that's pretty funny. I wanted to pause on that because I got a laugh out of that. So for the results, let's talk about the aerodynamic static coefficients. So these are the drag coefficient, the lift coefficient, and the pitching moment coefficients. So the drag coefficient for all configurations is really high. It's about 3. And to give you an idea of how high that is, the drag coefficient of a cube is around 1, and it's already really bad. So what would be the reason for such a high drag coefficient? I think the major reason is that there is just so much mesh, and that's because each wire has its own drag, but it also creates a back pressure and local boundary layers that significantly slow the flow in between these mesh parts. So effectively, even though you have such a small cross-sectional area, you have like a artificially higher cross-sectional area because of all this boundary layers being formed and all this blockage that's happening. So I think that's increasing the drag coefficient dramatically, well above 1 to like 3. That's insane. Interestingly, when there were simulated people on the bridge, the drag coefficient jumped up all the way to 5.8. So this value is so high that I'm not even sure that's correct. It's higher than anything I've seen. So it might be correct, but 5.8 is ridiculous. I've never seen anything like this before. So another interesting thing about the drag coefficient is that it doesn't really change too much with the changing angle of attack. So remember how I said that they were simulating the flow coming at an angle up or down compared to the bridge and also in line. So the angles of attack range from -8 degrees to 8 degrees. However, the drag pretty much stayed constant around 3.2 for that entire range. So the wind can be coming down at the bridge or from underneath, and the drag coefficient is relatively unaffected. Apart from the drag coefficient, though, the lift coefficient also shows some interesting results, namely that the lift is always negative, and by quite a bit. So that means that the bridge is actually producing downforce. So the lift coefficient is around -0.6 across the angle attack range, which, to give you an idea of just how much that is, you would need an ACA 0021 wing upside down at an angle attack of 6 degrees to get that much negative lift. And this type of airfoil is designed to produce a lot of lift. It's thick, which means that you're going to be producing a lot more lift at a low angle of attack, and pitched at a reasonably higher angle of attack, so 6 degrees. So this bridge is neither designed to produce much lift nor pitched at a high angle attack, yet it still produces so much lift, or downforce in this case. Interestingly, like the drag coefficient, the lift coefficient doesn't change a whole lot with changing angle of attack. So let's talk about the pitching moment coefficient now. Out of the 3, this one's actually the least eventful. The pitching moment coefficient is also shown, but it's also about 0 across the angle attack range. So it's quite well behaved. The drag, on the other hand, is incredible. I've never seen anything like this. I still can't get over how high it is. In addition to that, they tested the drag coefficient of an arch. So I mentioned how the bridge had like these arches going over the top, which you could then attach wires to give the bridge more more support. They tested one of these across different angles of attack as well, from 0 to 60 degrees. And the arches produce quite a lot of drag along low angles of attack, about 1.2. But once you get to 60 degrees, the drag coefficient drops to like 0.3. So this one's much more sensitive to, oh, I shouldn't say that actually. I should say that it's sensitive to very high angles of attack. The bridge deck that we saw before, we didn't test that high. Like you can see, they only went to 8 degrees. So in that range as well, the arch here is insensitive to the angle attack range. So we can't really comment on whether the bridge itself is more sensitive to angles of attack or less sensitive to angles of attack compared to the arch itself. Either way, the drag coefficients are very interesting for either one. Now let's talk about the dynamic responses. We talked about the static coefficients. Now talk about the dynamic situation of this bridge. So figure 13, they give the arch force time series and corresponding spectral plot for each pair of tests. So this time series just shows you the flexing, like the vibrations along the time series they had. And then they did a Fourier transform to get the frequency analysis, this frequency spectrum analysis of that. The first dynamic evaluation was performed according to the measured forces time by applying a fast Fourier transform to check the possibility of vortex shedding, which they mentioned here as VS. Now, VS in aerodynamics means vortex shedding, but in cognac terms, it means a certain quality. So cognac, for example, we can have different qualities. You can have VS, VSOP, XO, and a couple other terms. So that tells you how good the cognac is. But back to aerodynamics, it tells you how good the vortex shedding is, or how bad it is, rather. The significance significant amplitudes for higher wind velocities at angles of attack of 20 degrees and 30 degrees resulted in vortex frequency shadings of about 10 hertz. And this corresponds to straw numbers of 0.01, which is very low. And I'm guessing that that's probably due to the bridge having so many little wires in that perhaps the straw number is not as crisp as like just a regular cylinder, and there's some corruption there. But we can see here that the effectively the natural frequency, or the straw number, sorry, the vortex shedding is bang on 10, and it's very so let's move on to figure 16, which shows the damping coefficients for swing displacements. So the damping coefficient evolution as a function of both wind velocity and the angle of attack are shown in figure 16a. Its values are always positive with initial displacement, with drag playing a role in this behavior. So let's talk about this. This is interesting now. So the damping coefficient is always positive. Is that a good thing or a bad thing? Let's go back to divergence, what we're talking about, and flutter and galloping. So these properties, particularly flutter and galloping, to have them occur, you need to have negative damping, which means that the phenomenon is not being dampened. If anything, it's actually being excited. If you have positive damping, it means that it's trying to clamp down on this phenomenon and stop it from happening. So negative damping is good. And this bridge is displaying negative damping, which means that it's not allowing these aeroelastic instabilities to occur. So the divergence and galloping and flutter. And they say that the drag plays a major role, which indicates that those high drag values that we saw are actually very beneficial for the bridge. So having a drag coefficient of 3 is very good because it's producing a very positive damping coefficient, which makes the bridge safe. So in this particular case, the drag being so high is good. So that's having a high drag coefficient is bad, but here it's good. So in figure 17, we have the spectral peak coefficient. Sorry, the spectral peak component corresponds to a frequency that is always close to the first mode and to all other significant modes, with a spectral content below the peak occurring for wind velocities above 30 km per hour. Within this group, most of the high spectral components occur for frequencies clearly above the fundamental mode. The fundamental mode was 0.166 hertz. So they are clearly unable to excite the instabilities. So in other words, the fundamental mode was 0.116 hertz. The frequencies that they found here were well above that, which means that they can't excite these aeroelastic instabilities, which is good. The lower frequencies within the spectral content occurred at approximately 2 times this fundamental frequency, and this occurs for angles of attack between -6 degrees and 0 degrees. So again, that's too high to excite this fundamental frequency, which means that you're not going to be getting these aeroelastic instabilities. Again, the bridge is safe, in other words. So, in conclusion, the aerodynamic instability was evaluated by the damping coefficients all being positive, which is good, and for non-sinusoidal movement by comparing the most significant spectral energy contents of each test to the peak values. No aerodynamic instabilities were found, although upward and horizontal winds showed a significant displacement energy content for velocities above 30 km per hour, suggesting that the users may feel uncomfortable. So that's in this podcast. I hope you liked it. And if you did, make sure to like, subscribe, and tell all your bridge enthusiastic buddies. And if you want to get better at theory like this, for example, check out our courses. And if you want to get better, if you want to make your experiments more accurate, better as well, and your CFD validation data more accurate, which you're getting from either experiments or real life setups, check out our Atmosphere Hawk. It actually measures the density of air, which changes by about 2 to 4% every day. And most aerodynamicists, unfortunately, do not measure these values. And that means that their results are actually wrong. So if you want to make your results more accurate, check out Atmosphere Hawk. It gets rid of that error for you. And that's just a regular day, 2 to 4%. On other days, between weeks, between seasons, you can get high, you can get 10% error. So that's linked in the description. And I'll see you in the next podcast. Peace out, amigos.